Welcome back to Gale Force Wins Season 5.
Well, good evening, everybody, and welcome back to the latest episode of Gale Force Wins podcast. My name is Tyler Downey, and I'm going to be hosting, a couple of episodes coming up in the next little while. We're going to be working on a series of deep dives into some of the cool people and cool things that they do, many of whom are from right here in Newfoundland. Some are from Toronto. I've got one right here with us today who's from both. Dr. Anna O'Grady, astrophysicist, born and raised in Newfoundland, lived in Toronto, and now working at Carnegie Mellon as a postdoc. Anna, welcome to the show.
Thank you very much. I'm happy to be here.
So, tell us a little bit about yourself. How do we know each other? How did you get into physics? What's the story here?
All right. So I'll start with how I got into physics first. That's a little bit of a longer story.
Go for it.
I was always interested in science growing up. I was interested a little bit in biology and chemistry and a few different things. But what really sort of set my path along towards astrophysics was when I was in 8th grade. My mom and I were out doing some holiday shopping before Christmas, and I always love to get people books. So I was at Chapters and I was perusing the bargain bin table, and there was this big book on astronomy that I looked at, and I said, "Oh, that's interesting." But then I moved along, and I think I wandered over to like the dragon section of the bookstore.
That's a common theme with Anna. Yeah. I'll tell you that.
But my mom noticed clearly, and that book was under the tree at Christmas. So nice. This book was called The Illustrated Atlas of the Universe. It's about this big. It's one of these big coffee table books, and it's sort of pop astronomy. So explaining everything from the planets in our solar system to how our sun works to stars within our galaxy, the galaxy, all the way out to cosmology and how the universe is going to end. It explained all of that in a way that someone with like very basic, I was in junior high school, right, basic science background could understand. So I got this book on Christmas. It was like a thick, one of these big coffee table books, and I absolutely devoured it. Nice. I read it in 2 days. Something in my brain chemistry changed, December 25th, wow, 2008. And after that, I started reading things on the NASA website. I started, watching YouTube videos of Brian Cox and Stephen Hawking and Neil deGrasse Tyson and just anything I could get about astronomy. I asked my junior high school teacher, when I'm going into high school and, you need to pick which science you're going to do, yep, or at least that's how it was back then, which one is closest to science, to space science. And he said physics. So that sent me along there. And I have to thank all of the various teachers that I've had along this path, because no one discouraged me, even though, it's definitely a little bit of a niche topic to be getting into, especially in Newfoundland and Labrador.
Well, yeah, at the time, of course, there's very little astrophysics, although I think that has been changed a little bit lately, although we'll definitely be talking about that later.
That has been changed, yeah. So through high school, I was very fortunate to have an amazing physics teacher, Miss Amanda Walsh at the time, Amanda Craig now.
And where was this? Bishop's, right?
This was Bishop's High School.
This is Bishop's High.
Which is no longer.
No longer here.
Now retirement.
Yeah. You're dating yourself a little. Yeah, now it's a retirement home.
It's a retirement home. Class of 2012.
We're not even that old. It's just that's how fast things change these days.
But I had the opportunity to do some science fair projects, right, and Miss Walsh put me in contact with astrophysics professors at St. Mary's University in Halifax and at Mount Allison University in New Brunswick. Cool. So Dr. Robert Dupree and Dr. Louise Edwards, respectively. And that was my first contact with doing astronomy research. It was very simple stuff, stuff that, an 11th, 12th grader could do. But that sent me to National Science Fair. It sent me to the Perimeter Institute one summer to do a summer school for physics. And it absolutely solidified that this is what I wanted to do.
Now, if I recall, Anna, at that same time, there was another, perhaps we might call it an Ivy League institution that you were invited to join for a short summer. Can you tell us a little bit about that?
Yeah, so that was once I had joined MUN. Of course, you do general studies in your first year, and I knew that I wanted to do physics, but I reached back out to Louise Edwards, who was my mentor for one of my high school science fair projects. and just sort of just updating her, like, I'm at university now, I'm getting my undergrad, I'm going to do physics and math, this is great. And she said, Anna, we have this, she had moved from Mount Allison University to Yale University in New Haven, in Connecticut.
Yale University.
And she said, we have this summer scholarship program that invites, international young researchers to come and do like 6 weeks, 8 weeks, a few months research stints. You should apply for it. And I said, okay, not thinking that I was going to get it.
As we all do, as we all do.
So yeah, that was the summer of 2014. And that was really my first experience with like academic astronomical research. I was working with real data from this thing called the Dragonfly telescope. I was looking at galaxy clusters. I was looking for this sort of amorphous light that was in between the galaxies. And it wasn't a project that I ended up staying with, but it was really important because that taught me real astronomical research skills that showed me what sort of like a day in the life of an astronomical researcher really was super early. I mean, this was the year between my second and third year of undergrad at MUN.
Nobody that age gets that kind of opportunity to really see what it's like to work as a scientist,
Especially at that time.
Especially at that time.
This was kind of new. So yeah, that was sort of my first half of MUN was sort of just getting my feet on the ground, getting my courses done in this opportunity. And then in third year, that's really when I started to dig deep into the physics and math courses that were required for my degree. I started interacting with the Physics Society a little bit more. And I met this guy.
This one
guy, Tyler Downey. Yeah, we met in
2014.
2015.
2015.
Yep. No, 2014. I'm sorry. Yep. Fall of 2014. And it was that was the semester that I was doing 5 physics courses because I was crazy.
Yes, because you still are crazy, but...
So I think it was E&M.
It was.
I feel like it was
electricity and magnetism.
It was Legowski's
That's what it was.
E&M.
Yep.
That's when we first met for the first time.
That's when we met. So you would have been third year, I was fourth year. So my background is physics and math as well. Actually, that's how Anna and I know each other. I was the president of the Physics Society that year.
Yep.
And Anna was sort of a known quantity. She'd been to Yale. That was the thing. Everyone knew about her. So she started coming to hang out with us in our study group. And one thing led to another. And she was convinced by somebody to run for president herself. Became president of the society, and then I became president of the graduate society. And we had a bit of an unholy alliance there for a year where we tried to do a couple different things, working on various society initiatives. We used to make breakfast all the time for the department.
Physics breakfast.
The physics breakfast. And any physicist from MUN watching or listening to this today will absolutely remember.
You remember Haruki's pancakes because he did it the best.
He was the best. He taught me Haruki's pancakes. Haruki, if you're watching, buddy, best pancakes. So that's how we know each other. And that was 2015, so 2025, so we're on a decade now. Yep. And where has life taken you since you graduated from MUN? Where did you go next?
Yeah, so when I was in my final year of MUN, I was mentored by Dr. Ivan Booth, who's still at MUN in the math department, and Dr. Hari Kanduri, who has since gone on to McMaster. At the time, they were the only 2 people at MUN who were doing anything close to resembling astrophysics. They were in the math department, they were doing black hole research. So like the mathematical equations that govern the physics of how black holes work.
Yeah, people often think of black holes and think, oh, theoretical physics. Yeah, theoretical physics is math.
Yep.
That's what they do. So I remember doing a bit of work with Hari and Ivan as well. I took their classes. I used to go to the gym with Hari pretty regularly. I found that stuff so fascinating. I mean, I'm a math guy first, physics second. I think you're more physics first, math second,
a little,
right?
Yeah.
But I always enjoyed black hole mathematics. It's very, very complicated. I think I got a 62, but it was a great class. But anyway, so you did some black hole research with Hari and Ivan?
Yeah, so that sort of got my feet wet again in terms of astronomical research and, getting the experience required to apply to a graduate program. So either a master's or a PhD program that was focused on research. And it was useful because even though, I really enjoyed it, Hari and Ivan were amazing mentors, but comparing, the year and a half that I did on the math black hole research to the 2 months that I had at Yale doing observational astronomy, I really thought, I really liked it when I was working with real data, when I was this image has starlight in it. That's what I want.
That's what we're here for.
That makes something in my brain go,
So let's drill down on that a little bit. I think that's a really interesting distinction. Theory versus experiment and calculation. You want to talk a little bit about the distinctions?
Yeah, so a lot of physics you can sort of split between theory and experiment. In astronomy, you sort of get this additional aspect of it of observation. And there's still experimental astronomy. That's like LIGO and the gravitational wave detectors and neutrinos and stuff. And then theoretics. simulation, pen and paper theory.
It's the kind of stuff I did.
Yeah, and then there's sort of a fourth aspect to astronomical, which is instrumentation. So in astronomy, short of the few things like lunar rover missions and stuff like that, we cannot go out and physically interact with our things. You know, if you're a chemist, you can mix chemicals in your lab. If you're a biologist, you can go out and, survey animals or do things like that. But in astronomy, I cannot go out and weigh a star, unfortunately. I wish
We're
I
not
could.
quite there yet.
Yeah.
The scales just aren't big enough yet.
But yeah, everything is too far away. So we rely on understanding the light that's coming to us from all these distant objects, and we do that with telescopes. So we have instrumentation, theory, experiment, and observation. I do observation, which means that I am, either using archival data or taking my own data on telescopes and taking images of the night sky. Sometimes I'm taking images with telescopes that see in the same way that we do, so the visible light that we can see with our eyes. Sometimes I'm doing it with infrared light or ultraviolet or X-ray. I did some stuff on an X-ray telescope recently. It's weird.
X-ray telescope does sound weird, yes.
Weird. Yeah. So we work with real data, the light from stars or galaxies, and try to interpret what we're seeing. People who do theoretical astrophysics take sort of the fundamental physical equations that govern the universe. So how do stars work? What are the physics equations, the basic laws of thermodynamics, electrodynamics, cosmology, etc., and try to make predictions. And there's this great back and forth between observational astronomers and theoretical astronomers where theorists will tell me, hey, these are the interesting stars or galaxies that we think should be out there, but we haven't seen them yet. These are the things you need to look for. And that will tell me, that will guide how I derive my observing campaigns, what things to look for. On the other hand, I'll do observing campaigns and I'll find some weird stuff. I'm like, I don't know what this is. Theorists, here's the data, here's all the things that I found out about it. What do you think that this is? Yeah. And
so you talk to each other, theorists, observational, experimental people, they all chat with each other and figure out, sort of learn from each other and move science forward together.
Exactly. Yeah, cool? There is a true, and I got the appreciation from that by doing, I'm an observational astronomer, but I have this little bit of experience with a couple of projects in theory, and it gave me an appreciation for it. So, yeah.
Yeah. So the number of questions we could ask is infinite. So I think I'll just limit it to this. You finish fourth year, you go and you do your grad studies, and you sit down, and what we all know about grad school is that you have to sit down, you have to write a thesis. Right? Now, yours was a little bit different because you actually wrote 2 papers, didn't you, for your PhD? I wrote,
a few papers, but on 2 very different topics.
That's right. So why don't you tell us the first one? I think it's Thorn Jov objects.
Thorn Jov objects.
Okay, I got it right.
Yeah. What was supposed to be a short paper that ended up being the vast majority of my thesis. So I did my PhD studies at the University of Toronto under the supervision of Drs. Brian Gainsler and Maria Trout. So my thesis was going to be focused on essentially rare stellar populations. So groups of stars that were strange or different in some way, or there are not very many of them, and using observational data across the wavelength spectrum. So not just using what our eyes can see, but ultraviolet, infrared.
X-ray in some cases.
In some cases, yeah.
Although not in this one, I think.
Not for this one, but for later ones. But using all of the observational data to basically understand what these weird stars are. And at the very beginning, after I'd completed my first sort of intro year, Maria, my primary supervisor, came to me and said, I have a project that's really interesting and I think it'll be a nice short paper. Famous last words. And I'm guilty of this too. I am now guilty of this myself.
It's a scientist trait, I think.
It truly is.
Yeah.
There are these things called Thorn Jov objects.
Right.
The idea behind this is essentially a stellar turducken.
A
star within a star.
Right, okay. And then there's a turkey or a chicken all around it, I guess.
Exactly, yeah. A cosmic turkey, yes.
A cosmic turkey.
Turkey's all the way down.
Turkey's all the way down. See, this is the quality conversation you can expect from an astrophysicist. So, star within a star.
Star within a star.
So what do you mean by that?
So, there are various stars. Our own sun is something that we call a dwarf star. Stars that are on the main sequence. They burn hydrogen to helium in their core. They're very common. We have a lot of them in the universe.
These are your normal garden variety stars.
Bog standard star, dime a dozen. Stars like our sun, and particularly stars that are a lot bigger than our sun, when they get closer to the end of their lives, they will swell up into something that you might have heard called a supergiant.
Yes, I'm familiar with the giants.
Yes. Supergiants then, when they reach the very end of their lives, they're burning up through heavier and heavier nuclear fuel. They burn hydrogen into helium initially, helium into a suite of carbon, nitrogen, and oxygen elements, and those into heavier and heavier elements until you get to iron.
Right.
And iron, the periodic table works in such a way that iron is the first element that when you burn it, you lose energy instead of gaining energy.
So everything wants to become iron, I guess.
Yeah, and that's bad for stars.
Right.
We know when they're fusing hydrogen together, you get a little bit of energy out of that. That energy of nuclear fusion is what causes the light that we see from our sun. That is why our sun is glowing.
So just trillions and trillions of these tiny little energy emissions.
Yeah.
And that's what powers our sun.
Yes, exactly.
Amazing.
Yeah, and those nuclear reactions continue, but iron is the first one that when you fuse iron, you lose energy instead of gaining a bit of energy.
Right.
Well, it does continue. The star has no way of stopping it, and this is a runaway process where it's losing energy. It's losing sort of these robust nuclear reactions that are clattering around in the core of the star. That's losing pressure. That's keeping all of this material above it held up into a star. The star will collapse. All that material crashes onto the very thick, very dense core.
Right.
Rebound effect happens. This is a supernova explosion.
Wow.
That rips the star apart.
Yeah.
But that core that's left will survive in a lot of cases.
We have a name for it, don't we?
Yes, so there's two things that can happen. If the core is really big, it'll become a black hole, which are super interesting, and I know people love black holes, but I'm not going to talk about
That's
black
not our
holes
topic today. That's right.
The biggest stars that are a little bit on the smaller end of the big star range, those will become something called a neutron star.
Right.
Which is quite literally what it says on the tin. It is a condensed ball of neutron material.
So neutrally charged.
Neutrally charged,
really,
one of
really
the
dense.
Fundamental particles, and extraordinarily dense. A teaspoon of neutron star material weighs as much as the entire Rocky Mountain chain.
Wow.
A little teaspoon.
So don't eat it for breakfast.
Don't eat it for breakfast.
That's not
You're going to have a bad time.
Not a bad time.
Yeah. So back in the early days of astronomy, people were actually trying to figure out what powered the sun.
Right.
An early question back in the 30s was, why is the sun glowing? We didn't know. This was one of, we come to understand these things. And one of the proposals was actually that we had known about dense neutron materials for a while through nuclear fusion studies.
Right.
And one of the thoughts was that, what if there's a dense core of neutrons inside of our sun? And that's what's causing the nuclear fusion reactions. That turned out to not be true. It was Cecilia Payne-Kokoschkin's eventual thesis that found out that it was hydrogen fusion that was powering our sun.
Right.
But this idea of this dense core of neutrons powering a star, it went away from the public consciousness a little bit in astronomy, but then in the mid-1970s, two astronomers, Kip Thorne and Anna Zhikov, maybe you can tell by their names, thought of something
Where we're
kind
going
of crazy.
with this, yeah.
Basically thought to themselves, if you put a neutron star inside of a large star, we knew that it wouldn't work for a star the size of our sun, but if you put it into a bigger star, like a supergiant, would that star survive? Could that star maintain nuclear fusion off of all this neutron-rich material within it?
What an interesting question to study for your thesis.
Yeah. In the 1970s, Kip Thorne and Anna Zhikov, basically, they did the hard math of saying, yes, actually, this should be stable. If you can get the neutron star inside of the red supergiant, which people later figured out how that process happens, but if you can get it in there, it should be stable. And one thing in particular that was worked out then through the 80s and 90s was, it'll be a red supergiant, and there's a neutron star inside of it. But from our perspective, all stars just look like little points of light on the sky. How do we tell the difference between this red point of light, that's just a normal red supergiant, this red point of light, that has a neutron star inside of it?
Right, yeah.
How do you tell the difference?
And that is the focus of actually determining whether they exist or not. So theoretically, they may exist.
Yeah.
But theoretically, white holes, the opposite of black holes, could exist.
But
not necessarily. Right, we've never seen them. So just because the math says something should be real doesn't mean it is until we observe it.
Until we observe it. So,
and as an observationalist,
that's where we come in.
Uniquely suited to the task.
Yeah, so the theory was made in the 1990s as to essentially the flux of neutrons at the core of the star. So instead of hydrogen fusion or carbon fusion, there would be neutron fusion at the core of the star.
Right.
And that area around the neutron star would be so hot it would essentially enable nucleosynthesis, nuclear fusion that doesn't happen in normal stars.
Right,
So you get weird elements.
So this is a process that's supposed to be dead for the neutron star.
Exactly.
And yet, if it's hot enough and surrounded by
By
material,
all of this neutral hydrogen material, it has all of this star on top of it that
Right.
it can eat essentially
Cool.
and turn into these new elements. So it's thought that you could see if you saw a red supergiant that had molybdenum, rubidium, these weird elements that don't appear in normal red supergiants. That was the telltale sign.
further down the periodic table, some of
Exactly.
the odd things.
Yeah. And in 2014, it was thought that so 2014, this was when I was at Yale.
Yep.
So this research group led by Emily Levesque from the University of Washington in Seattle, they found this star called HV2112, which I'll get to why that's funny in a second, why the name is funny. It's called HV2112, and it is located in the Small Magellanic Cloud.
Right.
For us Northern Hemisphere people, you've never seen it unless you've traveled to the Southern Hemisphere. The Large and Small Magellanic Clouds are these satellite galaxies. They're these little puffy galaxies that orbit our Milky Way in the exact same way that the moon is this little satellite of our Earth and orbits
Right.
around it.
Makes sense.
So they found the star in the Small Magellanic Cloud, HV2112, and it was a red supergiant, and it had the element signatures that said that it should be a Thorn Jov object.
And was it? Yeah, that's where we are.
Yeah, so I came on to the scene in 2016 I joined the University of Toronto, and then 2017 I started working on my thesis research. And my supervisor Maria pointed out that if you looked at the light from the star, not the elements, but the light, and looked at how the light changed over time. A lot of stars actually are variable stars. Their light changes over time. If
Right.
you have a dimmer switch in your home, just sort of gently turn it back and forth, dim, bright, dim, bright. That's what a variable star does.
Right, okay.
It literally changes its overall brightness, its luminosity. For some stars, it happens on the order of days to weeks. For some stars, it's on the order of years.
Right.
HV2112 had a 2-year period. It went from bright to dim back to bright again over the course of 2 years. And it had a really weird shape. It had these twin peaks in
Right.
it that is rare in these types of stars and especially not expected for a normal red supergiant. So Maria's suggestion was I could use other archival light curve data to search for other stars that had the same weird light curve as this possible Thorn Jov object,
Right.
HV2112.
Take a profile and match it and see if you can find another candidate.
See if you can find other candidates, because the thing with HV2112 is that people were digging into it exhaustively.
Right.
While I was working on this project in 2018, another paper came out that suggested that HV2112 wasn't a Thorn Jov object at all, that you could explain its element enhancement by it being something called an AGB star, which is a particular type of giant, not
Right, not a
supergiant star.
supergiant.
So there's controversy, there's debate, as there is in astronomy.
Any good science has debate.
Exactly, yeah. That then started my journey on finding other stars that looked like HV2112, because if we can find more than just the one star, that opens up, not only do you have more examples, so if HV2112 is a weirdo for some reason, you can find other things of the same class to compare it to, and also then you can do population statistics. Thorn Jov objects are they have such a weird evolutionary path to being born, you can actually predict how many you would expect to be in a galaxy.
Right.
So do we find more than that? Do we find less than that?
Just statistically, I guess.
Yeah.
You'd say, there's got to be at least 12.
Yeah,
It might be more than that.
yeah, more or less.
And more or less 12.
So yeah, that's what I started to work on. The funny bit, just totally,
Yeah.
it's total sidebar here, but I was telling you about this project when I
Yep.
started. I was like, yeah, the name of the star is HV2112, and you're like, 2112? That's the name of my favorite Rush
My
album.
favorite Rush album. Any Rush fans out there in cyberspace, 2112 is probably their greatest prog masterpiece. I could talk about this all day, but I don't want to waste the valuable time we have with Dr. O'Grady. So instead, I think what I'll ask you about is how did the search go with HV2112? Did you find any candidates that looked good?
Yeah, so we found 12 other stars that looked...
What are the odds? Almost like I knew ahead of time.
12 other stars that looked so similar to HV2112. They had the same light curves, they had the same temperature, etc. I got the huge privilege to travel to Chile, to Las Campanas Observatory, and observe on one of the twin Magellan telescopes.
Fascinating.
These telescopes have 6.5 feet mirrors. And I thought of that, I saw pictures of it, and I thought to myself, okay, I think I have an idea of how big that is. And then I actually got down there and saw it. And I can make this joke here because, fellow Newfoundlanders, this joke only works with a certain demographic of people. You know how you think you know how big a moose is?
Oh, yeah.
And then you actually see a moose and you're like, oh. That was like me in this telescope.
The moose of telescopes.
Yes, it's bigger than you think it is.
Huge.
Yeah. So yeah, I had the huge privilege to go down there, and we took spectroscopy of all these stars. We were looking for these elements. Spectroscopy is the process of, the Pink Floyd album with the prism and the light.
Oh, you mean Dark Side of the Moon? You know, we listened to that in the car on the way here, actually.
We did.
Yep.
Separating white light out into all of its constituent colors.
Right, like the rainbow prism.
The rainbow prism. That's what spectroscopy does. You're separating light out into all of the various wavelengths as deep as you possibly can. And you're essentially looking for little signatures in that light that indicate that a particular element is in the atmosphere of a star.
Oh, wow.
And each element has its own unique fingerprint that will show up in the prism of light in a certain way.
So sort of like a needle in a haystack, a galactic haystack, if you will.
Exactly, yeah.
Wow.
Yeah. So we looked for these weird elements, the rubidium, the molybdenum, etc., that should be in Thorn Jov objects. We did see them. But this sort of lingering question was still lingering over the project, which was this other paper that suggested, no, you can get these elements also in these stars called AGB stars.
Right.
And in particular, the most massive of these are called super AGB stars. And super AGB stars, I'll just explain this briefly. I mentioned stars that explode as supernovae.
Yes.
The supergiant stars.
Right.
Our sun won't do that. It'll puff up into a giant star. It'll leave its outer layers behind, becoming a planetary nebula and a white dwarf.
Right.
So you can broadly divide all stars into low mass stars that will produce white dwarfs and high mass stars that will produce other compact objects, neutron stars or black holes.
Cool.
And the tipping point, if you ask any astronomer just publicly, oh, well, what's the mass? At what point does a star jump up into, it's going to blow up as a supernova? And we'll all say 8 solar masses. And that is...
So 8 times the mass of our sun.
8 times the mass of our sun, yeah. And that is... that number is actually not known to that precision at all.
No, of course. It's just a number to throw out.
There's a number to throw out, yeah. There is...
It's not 1,000 solar masses. It's not 0.01 solar masses. It's like 8 or 10.
Somewhere around, in the range of, we'll say, 7 to 12 solar masses.
Right.
And the point at which that tipping point can depend on the environment the star is in, the environment it was born in, all of these things. So these super AGB stars, these are essentially the stars that sit directly over that seesawing point.
Oh, wow.
Low mass super AGBs are the biggest stars that will not explode as supernovae.
Okay, cool.
And the highest masses of super AGBs are the tiniest stars that will explode as supernovae.
Wow, so they
sit
provide a
right
limit
on this seesaw.
Cool.
So there was this vague thought that H3112 might be a super AGB star instead. So getting back to the research that I did, I found these 12 other stars, so 12 to 13 in total. Myself and my colleagues threw the kitchen sink at them in terms of analyses. This is something of a brand that I've discovered that I have, which is thoroughness. When it comes to academic pursuits. So what was supposed to be a quick paper at the beginning of my thesis turned into a 32-page behemoth.
Wow. But thoroughness is a great quality to have in a scientist, right?
It ended up being useful in this state because only through going through all of these options exhaustively. And I actually connected with a theorist, Jim Fuller and Evan Bauer, who do a lot of work on stellar modeling. And they basically came up with a really novel way to measure the mass of the star.
Cool.
So how much the star weighed. I mentioned earlier that I can't go out and just plop a star on a weight scale and measure it, and I wish that I could. The mass of stars is one of the hardest components to measure.
Right.
It's
you
very,
wouldn't
very
think, it's
difficult.
kind of odd. You wouldn't think that because, this coffee cup, I can tell how much this weighs. We can figure that out pretty quick. Weight, mass should be easy, but it's actually so very complicated for something that's so far away. Yeah,
it's one of the hardest things. But my theorist colleagues came up with a really novel way to do it. And one of the really important, the issue that we were having was that for a lot of properties, like the elements in them or what color they should be, Thorn Jov objects and super AGB stars, despite being completely different types of stars, they shared a lot of similarities.
Right, yeah.
But one area where there was actually this divergence was the mass. As I mentioned, the super AGB stars are on that tipping point. So they're all around 8 to 10 times the mass of our sun. Whereas there is a strong theoretical backing that Thorn Jov objects have to be at least 15 times the mass of our sun.
Wow.
They need to be that big. If they fall below that mass, they actually lose the pressure gradient, essentially, that allows them to undergo nuclear fusion, and they would collapse.
So even the biggest possible AGB star isn't big enough to be a TZO.
Exactly.
Is that correct?
And the smallest TZO can't possibly be a super AGB. There's this gap between them.
So as long as you can measure the mass accurately, you can tell the difference between these two things.
Exactly.
Wow.
And that's what we did. I worked with my theorist colleagues, and we came to an understanding of what the mass was. And for all of these stars,
Drum roll, here we go.
including HE212, they were all too small to be Thorn Jov objects.
Wow.
Which initially was disappointing to me.
Yeah.
I had all of this time on like the paper draft that I was writing. It was like the discovery of a population of Thorn Jov object candidates in Magellanic Clouds, and I had to be like, no. But
that's the beauty and magic of science.
yes,
right?
it was still super important. No results are still important.
Yep.
That you don't find something is still important. And in this case, we didn't not find something.
No, that's right.
Before I put out my paper, there was only one other candidate super AGB star known.
And now there's at least 14.
And now there's, we increased by an order of magnitude the number of these stars.
Yeah.
So for my first research project, it certainly took longer than I thought it would. And it went in a direction that I didn't think it would go at all.
Right.
But as you said, that's the beauty of science.
Absolutely.
And when we will pose a hypothesis, essentially I had a question and I posed a hypothesis that these new stars that I was finding were Thorn Jov objects. And I was wrong.
Yep.
But that tells you something about it. And when we embark on these scientific questions, we follow where the data takes us, not necessarily where we want it to lead us.
Right.
And that's why, sometimes we change our conclusions, we change our hypotheses, we change our minds, quote unquote, in that, we are just trying to decipher what is true. And in this case, literally just what the starlight is telling us.
Right.
There's a truth there, and you just need to dig hard enough until you understand what it's trying to tell you.
I love that. And I think that there's something really deep there, which is some of the best, most important results in science, and physics especially, are not sought intentionally. The speed of light being constant. Michelson-Morley experiment. You and I have studied this for years.
Yep.
The idea that there has to be some sort of ether out in the universe somewhere that light has to travel through. Light can't travel through a medium because it's a wave, and we all know waves are like water or a string, right? Space can't be a wave.
Yeah.
But of course, we know that that's not true. There's gravitational waves. There's light waves. There's all sorts of wave-like behavior, and they set out to prove that there absolutely must be an ether. And Michelson and Morley were wrong.
They were wrong.
They confirmed that the speed of light was constant. And who did that inspire, if you might recall, Anna? What scientist took that result and ran with it?
Einstein.
It was Albert Einstein. Albert Einstein was only able to do his work because of the work of Michelson and Morley. And that is the beauty, I think. And that's what I love about science is, I'm wrong more than half the time. Like when I talk about science, I teach it. I like to read it. I like to learn it. But I'm not always right. And sometimes you're wrong in ways you couldn't even imagine because it's just such a complicated field.
Yeah.
And that actually is the beauty. I love being wrong.
Yeah.
I love being wrong in these situations. And I'm sure, as disappointing as it was at first, you're glad you were wrong too.
Yes, absolutely. It taught us new things. I always like in trying to figure out a question in science to digging down into a rabbit hole.
Yeah.
And you get to the bottom, you're like, oh, okay, I'm at the bottom. And then you turn around, and then there's another rabbit hole in the wall
Going
of that
that way.
first rabbit hole going a different direction. There's never
There's never done.
You're never done.
There's nothing ever done.
Yep.
And I think that, not to get too deeply philosophical here, but that's a real good model for human knowledge in general.
Yes.
There's more on this earth than we could possibly learn in one lifetime. Yeah. There's more on this earth than humans can live in one species time. So let's get to work. Let's do it. Let's be wrong. And let's come up with some really, really interesting physics.
Yeah, and to me, that's part of what inspires me to study it in the first place.
Right.
Is that studying astronomy, I think, just by way of having been in the industry, quote unquote, for nearly a decade.
The old star industry.
The star industry is that I do have a unique perspective on how big the universe is and how small we are.
Right.
And that to me is good. That we can't possibly understand it all. So any little bit that you do understand is worth it because it is, it is also infinitesimally large.
Right.
And you are so infinitesimally small that any progress you're making towards understanding more of our place in the universe, how the universe works, are we alone? Mm-hmm. Where did we all come from? As a cosmological standpoint, there is inherent value in that. because we are all stardust,
That's
to
right.
quote
Yep.
Carl Sagan, and we are literally the universe trying to understand itself. And that's why I do it. Like, people ask why, and I'm like, it's because my mom bought me this one book that changed something in my brain, and when I look up at the stars, like, I literally feel something in my brain expanding of like, that is an infinite cosmos out there, and I have the privilege of being in the job that I am, where I get to take the light that comes to us from those stars and open it up and understand it.
Wow.
And I'm like, yeah, that's like the coolest ever.
I think that's an absolutely beautiful sentiment. I completely agree. I think it's why any of us do anything is that we're motivated by passion. We're motivated by beauty. We're motivated by the idea that something so infinitesimal can understand something so infinite. Yeah. And even if you only understand a little bit at a time, you're still batting way higher than your little piece of the universe. That's for sure, right? So, Dr. O'Grady, before we wrap up, would you just finish telling us about your career? Where are you now? Where have you come since the University of Toronto? Any work on TZOs we can expect in the future?
Yeah, so not so much TZOs. So what I wanted my thesis to be on was understanding strange massive stars, the big stars, the supergiants. And then I ended up finding super AGV stars, which, as I mentioned, are on that tipping point between low mass and high mass.
That sideways rabbit hole, if you like.
Sideways rabbit hole. And I'm like, okay, I backed myself out of the rabbit hole. I'm like, let's redirect. So I started at the end of my PhD to work on a project on yellow supergiant binaries.
Okay.
So if anyone's seen Star Wars, that bit in A New Hope, that bit in A New Hope where Luke stands on the farm looking out at the twin suns of Tatooine. Tatooine is in a binary star system.
Okay, so binary means two stars.
Two stars orbiting each other.
Right.
It turns out in the recent decades, it has become very clear that binary stars are ubiquitous. Among massive stars, they're absolutely everywhere.
Wow.
If you start to look at stars that are like 10, 12, 15 times the mass of our sun, we are realizing that basically 100% of them are in binary systems.
Wow, really?
Yeah, which is a complete paradigm shift
different,
to how we used to think about stars.
You'd think of stars as just being one lone star floating around, right?
Exactly, yeah. But when it comes to massive stars, they're all in binaries. Some of them are in triples, which that hurts my brain. I don't think about that.
Well, the three-body problem comes into play, and that's a great show.
Yeah, but I started to work on yellow supergiant binaries and trying to basically cohesively, holistically identify all of them in the Magellanic Clouds. The Magellanic Clouds have become kind of my playground.
Right.
So I graduated with my PhD in 2023.
Wow, congratulations.
Thank you. And then I was lucky enough to be offered a postdoctoral fellowship at Carnegie Mellon University in Pittsburgh.
Wow.
Which is a different place to live. It's sort of a mid-sized city, so kind of cutting the difference between
Toronto and St. John's.
And even St. John's. I grew up in Killbride. Right. I grew up on a farm in Killbride.
Killbride proud over here.
Killbride proud. Moving from that to the biggest city in Canada, I like Toronto, but there was definitely an element of like, this is too big, there's too many people, I feel kind of claustrophobic. Pittsburgh has been really nice. It's a mid-sized city. It's cozy in that way for my temporary journey from Canada.
Plus you got football, you got hockey,
You have all the sports, truly, in Pittsburgh.
Got Always Sunny in Philadelphia is not that far away.
Not that far, yeah. Home of Mr. Rogers.
Home of Mr. Rogers.
Neighborhood. Actually, the neighborhood across from me. I live in a place called Shadyside. He lived in Squirrel Hill. It's just down the street from me.
That's pretty cool. Actually, I didn't know that.
So I'm living there now. I've been there for a little over a year. And I'm continuing to work on yellow supergiant binaries. I recently just got into a collaboration, somewhat by chance, but an interesting question about Betelgeuse, which, not the movie, but the star, the closest red supergiant to Earth. There were a couple of papers, a couple of academic articles that came out fall last year that posited that Betelgeuse is actually in a binary, that it had a companion, heretofore unseen until this point. And I jumped at that and I said, that's a massive star. It's maybe in a binary. I want to know more about it. I reached out to myself and my collaborators at Carnegie Mellon. We reached out to the authors of the study and we're working on some really interesting stuff right now. That's the stuff that I talked about that I've discovered that X-ray telescopes are really weird.
On from infrared into X-ray. That's the next step forward.
I'm slowly just covering every aspect of
every possible element of the electromagnetic spectrum.
The spectrum, yeah.
So eventually you'll have to be microwaves and
radio and gamma rays, and then I'll have collected all of the gym badges.
That's how it works. See, I still know my electromagnetic spectrum, thank you very much. I haven't been out of school that long. So that's what you're working on, yellow supergiant binaries.
Yeah.
Wow.
And Beetlejuice on the side.
And Beetlejuice on the side. Well, folks, I mean, if that doesn't sound like a full plate to you, then I really don't know what, I mean, that's a full plate of jigs right there. So, Dr. O'Grady, thank you so much for being here with us today. That was a fantastic discussion. I'll leave it up to you if you want to have any final thoughts on science and why it's important to us.
Yeah, so I'll loop back to something actually. I mentioned that when I was going to MUN initially, there wasn't a whole lot of astronomy there. There was just a couple courses.
Right.
I was working in the math department on black hole science, and that has changed in recent years. We have a professor, Dr. Hilding Nielsen. He's joined the department. He does astronomy. He does observational astronomy like me. And I visited the university back in March to give a seminar talk and to give a talk at the Geo Center. And through that, I met Dr. Nielsen in his group. And suddenly there went from being basically just me and Riley doing black hole stuff to there's still people doing black hole stuff at MUN, but now there is this huge group. It's, I think, the biggest group in physics.
Wow.
All working with Dr. Nielsen on astronomy.
Yeah,
and
short
I was
10 years.
in that short amount of time. And I was like, I was so happy I could cry because I thought that I was never going to see this, that it was too different. It wasn't what MUN had focused on.
Right.
And I already just see, and a lot of those students came out and participated in the eclipse outreach when the eclipse came through Gander and came through our island in April.
Now, were you somewhere during that eclipse?
I was also in Gander.
No way. In Gander, doing what?
In Gander, I was helping. Some people may have seen me. I got to meet someone very cool. I got to meet Eddie Shearer.
Oh, yeah.
He interviewed me for that.
He's as cool as it gets.
He is very cool.
He's a cool guy.
But, just seeing, like, basically this multitude of students so interested in, and yes, I'm biased, I love astronomy, so that's what I'm going to focus on, but seeing that blossom here already has just made me so happy. And I think having this diversity of scientific inquiry, of different, fields is, I really think only good can come from it. And, as I said, some people want to get into it because they're interested in the computation and the computing skills it'll give them, and some people are interested in the questions and the answers. But I just truly think having that space for people to follow their passion, especially in science, like you think it's, I don't think a lot of people think this now. I think it was sort of an older sort of thought that, arts are where all the passion is and science is all like cold and calculating and, people in lab coats and so on.
It doesn't need to be like that.
But it doesn't need to be like that at all. And I'm rambling here. I'm totally.
It's all good.
You know this.
I understand the passion. I mean, like I went into physics, and many of you know now I'm no longer working in physics. I actually work in municipal politics. But I found my passion in science. I found my passion in politics as well. And I also find passion in theater and music, right? It's passion is where you find it.
Yeah.
And I think that's a fantastic closing message, folks, from Dr. Anna O'Grady, our very own homegrown astrophysicist from Killbride. She's chasing her passion at Carnegie Mellon, and we hope that you do too.
Thank you for tuning in to Gale Force Wins. That's Gale Force Wins, WINS.com.